This is GMATS 41. You are welcome to our circuit theory class. Previously, we established the effective resistance for a series network. We also established the effective resistance for a parallel network. We were able to solve problems for each case. In this video, we now direct our attention to series parallel network. A series parallel circuit is one that consists of a combination of both series and parallel network parts. So you have the circuit element, either it is a resistive circuit element or it is an inductive circuit or a capacitive circuit, where you could see the circuit elements arranged both series and parallel. You cannot tell if the circuit is a series network or if it is a parallel network. So such circuit is what we call the series parallel circuit. When you are required to obtain the effective circuit element there, okay, we are concentrating on resistance for now. We shall trade that of inductive and capacitive subsequently. When you are to obtain the effective resistance, what is very important for you to know? It is important for you to be able to identify the way these elements are arranged in the circuit. Get to know their relationship in terms of their series parallel connection. Once you're able to identify that, the next thing you do is to remember that when you are resolving this circuit, you resolve towards the source. The source here is this cell. Is that okay? So you're going to resolve this resistive network towards the source. We'll have this example here, this circuit containing 4 resistors. And now you notice that some of the resistors are connected in series, others are connected in parallel. So I'm going to check the relationship between these and then resolve them in order to obtain the total or effective resistance. How do we do that? Looking at this, you notice that R1 and R2, they are in series. And then you notice that R3 and R4 are parallel. How are we able to identify that? Look at this cell supplying this current. You notice that this current will pass through R1, the same current will pass through R2. Because this is a linear network, they are series. You're getting that right? So this current will enter through R1 and R2. But once it gets to this point, this is a principal node, a junction. What is going to happen? The current will split into 2 parts. One will take this upward path, while the other will take the downward path. So we're going to have I3 and I4. So you notice that this part of this circuit divided our currents that approach this junction. And that's why the resistors we have here are in parallel. So we're going to resolve them in parallel, resolve these two in series, and then see the relationship between these series resistors to these parallel resistors, which will now work to get the total or effective resistance. So let us quickly check how we resolve these. Okay, I decided to add up R1 and R2 first because they're in series directly as you see that. So Rs, which is series resistor, is equal to R1 plus R2. Recall that if you want to obtain effective resistance in series, you just add up the resistors values. Is that not so? And so we have an equivalent circuit, which is this. We still maintain this parallel resistive part. At this point, we're now to resolve these two parallel resistors, and now when you resolve them, you're going to get this. R parallel, that is parallel resistance, is equal to R3 times R4 divided by R3 plus R4. We established this when we derived the formula for calculating effective resistance for parallel network. And so on resolving these two, you notice that this whole parallel network will be replaced with RP, which gives us this arrangement. This is an equivalent circuit to this. This is an equivalent circuit to this. You now notice that Rs and Rp are in series, isn't it? So you can add them up to get the total or effective resistance. That's what we'll add up to get R total equal to Rs plus Rp. And this is the final resistance network that has been obtained from resolving this. In the next video, we're going to pick questions to solve and then see how we handle problems of this kind. We now have this question on the board. Compute RT, that is R total, in the figure below and obtain the total power in the circuit. Now if you look at this circuit, it is a series parallel resistive network. Because you can't say that this is a series resistance arrangement. You can say it is parallel resistors arrangement. You can say that the connection between the resistors, some are in series, others parallel, so it is series parallel resistive network. Now to solve this problem, we first have to identify the relationship between these resistors. How are they actually linked? And for us to get the relationship, we need to know the way how current moves in this circuit. Now watch, you know that first of all, this cell will produce a total current which will come out, the current will move this way. Coming to this point, it will divide into two because you have a resistor this way, you also have another resistor this way. So we'll have the current splitting into two at this point. Therefore, these two resistors are in what? Parallel. Let's take note of it. Then parallel. We can call it R. Let's call it RA. Okay? Let's call that RA. And then we come over here. We also notice that this current, when two of them come to this point, they will combine and move serially. But then at this point, look at it, there is another principal junction there because you have resistors in this direction. You also have resistor in this direction. So the current will split into two. One will go this way, the other will go towards the right hand side. Once again, what does that tell us? That this resistor here is in parallel with the resistors you have here. Is that okay? Now, when the current that is entering this 4 ohm resistor get to this point, again it will split into two. One will go through this 6 ohms resistor, the other will go through the 3 ohms resistor. You see how the thing is moving, right? Which simply tells us that these two resistors are in what? Parallel. Since current divided there, let's call it RB. Okay, let's call what we're going to resolve here as RB. Having done that, may we still label each of these resistors? Let's have this as R1, this as R2, this as R3, we have this R4, R5, then R6. We can now solve. Remember, for series parallel network, you resolve towards the what? Source. So we'll start our resolution from here, coming this way. However, we won't solve this 3 ohm resistor together with this 4 ohm resistor in parallel for now yet. Why? You notice that the current entering this 4 ohm resistor, the same current shares and enters the 6 and 3 ohm resistor here. Therefore, we need to resolve everything that is happening here internally first. Is that okay? These two are in parallel. So let us obtain RB then. RB is going to give us R4 parallel R5. And of course, that is going to be, R4 is what? 6 ohm resistor. So that will be 6 times. R5 is 3, then divided by 6 plus 3. Okay, remember they are in parallel. And when two resistors are connected in parallel, you can use this formula, product of the resistors divided by sum of the resistors. If you work on that, what will this give to us? 2 ohms, because this is 6 times 3 all over 6 plus 3. Take note please, all these values of these resistors are in ohms, okay? They are in ohms. Now we have gotten this. Do you notice that once you resolve these parts, you get one resistor which is 2 ohms value. That resistor, since it is only one, it will now be linked with this 4 ohm resistance serially. Which means that RB, which is 2 ohms for these two solved together, is in series with our R3, which is 4 ohms. Let us call that RC. Let's call that RC. So RC will be equal to R3 series, for series use plus, you know that, right? Series RB. I've explained that already, why RB is in series with R3. Therefore, we can substitute our R3 by our label is 4 ohm resistance. So we put the 4 there plus RB, which we calculated to be 2. Add them together, you get 6 ohms. Did you take note that we are done with this internal component? We are done with it, okay? And what we obtained is what? RC. RC, and the value is 6 ohms resistance. At this point, that RC, which is all the internal resistances here, is in parallel with this R6. I explained that already that current will divide at this point. One will move downward, the other will go this way. So the resistor here is in parallel with everything you have internally here, which will got to be what? RC. We are going to call that component RD. So our RD will be equal to R6 parallel RC. R6 parallel RC. And we know that R6 by our level is 3 ohms, so that's going to be 3 times the value of RC, which is 6, divided by 3 plus 6. If you work out this, 3 times 6 is 18, divided by 9. That will still give us 2 ohms. Now, did you take note of something here? We have finished resolving everything we have here. We have finished resolving everything we have here. And the value we obtain there is RD, where the value of that RD is equivalent to what? 2 ohms. Now take note that these 2 ohms, which is RD now, only this single resistor will be connected to the arm coming out from this point. Is that okay? Which means that we now have this connected to this RD. I'm going to show you that. Just something like this. Then we have this. This point is connected to our RD. So this is our R9. That is our 9 ohm resistance and 6 ohm resistance together, which we already called what? RA. 9 ohms, 6 ohms. So what we are going to do now is to resolve these two in parallel, because they are in parallel, then add it to this RD. And we're going to do that right away. This is RA already, so RA is R1 parallel R2. R1 parallel R2, which of course is going to give us R1 times R2 divided by R1 plus R2. R1 is 9 times R2 is 6 all over 9 plus 6. 9 times 6 is 54 divided by 15. 54 divided by 15, if you divide that, that will be about 3 whole time. Okay, 0.6. 3.6 ohms. So our RA now is 3.6 ohms. And do you know that these two resistors now has been resolved to give us one single resistor? That resistor will now be connected to this arm coming from this direction. And so what we now have is something like this. This is what we have. Where this is our RA and this is our RD connected to the cell. So we can actually get RA total from this point now. RA total will now be equal to RA series RD, which will be RA was the value 3.6 and RD, what did we get? 2. If you add that together, you get 5.6 ohms. And this is the total resistance of this circuit. We're going to take a short break. When we come back, we'll calculate the total power using the total voltage in the circuit divided by square of the total voltage in the circuit rather, divided by the total resistance that we obtained. You are welcome from a short break. Now that we have calculated the total resistance for this circuit, we now want to get the total power in the circuit, okay? So the power absorbed by the circuit is what we want to obtain now. We know the voltage of the circuit is 16.8 and we've gotten the total resistance. Given such data, it means that power P, alright, power P will be equal to square of the voltage divided by what? Total resistance. And so this will be equal to the voltage, the total voltage produced by the cell there is 16.8. We are going to square it, then divide by the total resistance we calculated, which is 5.6. So let us work this out with our calculator. 16.8 squared divided by 5.6. 16.8 squared divided by 5.6. Good. It's giving me 50.4. And the units of power is watt. So this is the value of the power in the circuit.